Hi, I'm Gabe Moreno, and in this talk I'm going to be telling you about our project, Formal Arguments for Large-Scale Assurance, or FALSA for short. DoD needs to be able to deploy new capability with speed and confidence to adapt to changing missions and environments. Usually, this capability is obtained by evolving large-scale systems. However, assuring these systems to deploy them with confidence is a bottleneck to achieving that desired speed. This work aims to speed up the assurance of evolving large-scale systems through reuse and sound integration of diverse assurance analysis and rapid detection of non-conformance between system behavior and its assurance argument. To ground our research, we created a model problem that preserves the technical difficulties that this project tackles. It's based on a humanitarian mission that must be carried out autonomously by a UAV, and the goal of the mission is to deliver life-saving supplies in a disaster zone. We implemented this model problem in simulation. Here you can see a high-level architecture of this system. This system has multiple quality attributes concerned, including timing, safety, control, and security. Another important aspect of this system is that, as you can see in this component diagram, we have to integrate multiple components. Some of these components were developed by us, and others were off-the-shelf components, for example, that flight controller. What that means is that in terms of assurance, we will have different assurance results and different kinds of results. For example, for the mission manager that we developed, we can do formal analysis, but for the flight controller, which is an off-the-shelf component, we may have to resort to testing for its assurance results. All these characteristics are what make assurance with speed difficult in this setting. So there are different factors that hinder assurance speed. One of them is the lack of effective reuse of assurance results. And another one is the inability to integrate multiple types of assurance analysis with different levels of formality. What that means is that we cannot automatically and formally evaluate such an argument because the analyses are not quite integrated. And another problem is the lack of flexibility to adapt to changing missions and environments. The solution that we propose is to combine analysis and results that have different levels of formality in a formal assurance argument. You may be familiar with assurance cases, but those are intended for human evaluation. In this case, we want to create a formal assurance argument that ensures that the combination has a single interpretation, and therefore it can be automatically evaluated. Also, it can be developed incrementally, so we can start focusing on a part of the system that requires higher level of assurance and then move to other parts. And it's also modular so that it allows reuse of assurance results. In addition to that, we use runtime monitoring and data to detect whether the system behavior conforms to the assurance argument. And that allows us to deal with incorrect or changing environments or systems assumptions that may have been made when the assurance argument was created. That detection of non-conformance also provides the foundation for runtime enforcement and adaptation in future work. So now we'll look at the first part of the approach, which is reasoning about assurance when we have assurance results with mixed levels of formality. Let's look first at the different elements in an assurance argument. At the top here, we have a claim. A claim is a property or an assertion about the system. Then we have an analysis. An analysis is a procedure that, given that its assumptions hold, it proves or supports a claim. And then we have assumptions, and the assumptions are properties that must hold for the analysis results to be valid. Lastly, we have evidence. Evidence is data or facts about the system or the environment that are relevant to discharge an assumption. Here we have an example of all these elements put together. At the top, we have a claim that says that all tasks in the system meet their deadlines. Then we have an analysis, rate monotonic analysis in this case. That's a formal analysis that it's based on a number of assumptions. For example, that tasks have rate monotonic priorities and that the task parameters correctly reflect the tasks in the system. In addition, here we see an example of evidence. One of the assumptions of this analysis, RMA, is that tasks are scheduled with fixed priority. And in the evidence here that we have to discharge that claim is that the operating system is configured to use fixed priority scheduling. With those elements, we can build a formal assurance argument where multiple analyses are combined to guarantee high-level assurance claims about the system. For example, in our model problem, that the drone flies safe trajectories. Then assumptions are discharged with other analysis or evidence. And the argument can be built incrementally. For example, we can start with partial evidence and later on replace that with a result of some formal analysis. Now, analysis and evidence, they can have different levels of strength depending on their comprehensiveness. That means how many cases they cover, and the rigor, that is the method of obtaining the results. That method could be theorem-based analysis or model checking, which is exhaustive. It could be based on simulation, testing, or inspection, which are more on the informal side of assurance. Now, the strength of the analysis and evidence impact the strength of the claim they support. So what we want to be able to do is to compute the strength of a claim based on the analysis and evidence that support it. To do that, we use modal logic. Why? Because it introduces two important concepts to deal with this problem. One is the notion of multiple worlds, and you'll see that here we are dealing with multiple analysis worlds. And the other one is modes in which something can be true. And that's related to the strength of a claim. So modal logic has the normal elements of propositional logic, but in addition to that, it adds two modal operators that we see here in red. And these operators, for example, box A, mean that A is true in all worlds. And for now, think of that as in all cases. And diamond A means that A is true in at least one world. One example of modal logic that you may be familiar with is temporal logic. In temporal logic, a world represents the state of the system at an instant in time. Box means that a property will always be true, and diamond says that a property will eventually be true. So in our research, what we are doing is describing how to instantiate these modal logic concepts to represent different types of analysis and claims in a single logic system. So let's look at an example where we are combining elements with different levels of strength. In this example, we have at the top a claim. The claim says that the drone completes the mission safely and on time. And then we decompose that claim into subclaims. On the left side, we have that the drone completes the mission safely, and that is supported by an analysis, in this case, a safety analysis that is exhaustive. And on the right side, we have a subclaim that says that the drone completes the mission on time, and we show that that claim holds using simulation. So the question is, given this small assurance argument, what is the strength of that top-level claim? Is it a box, meaning that we can prove that it will always complete the mission safely and on time? Or maybe it's a diamond, meaning that with the argument, we can show that it's possible to do that. So the other part is when we add the modal operators, box for the exhaustive safety analysis and diamond to represent the possibility that we show with evaluation, then one important question is if the set of worlds for these modal operators are the same or not, and if that matters. And the other question is whether it makes sense to combine these two modal operators, given that they may have different worlds. So to use the concepts of modal logic in this setting, we have to start by defining what a world is. In temporal logic, time is the central concept. In our setting, system analysis is the central concept. There are multiple analysis domains that we use, for example, real-time performance, logic correctness, safety, physical correctness. Each analysis domain draws on information from the system, the platform in which it executes, and the environment in which the system is situated. And all this information that an analysis uses, we refer to that as analysis resources. So to use modal logic in this context, we have to take into account that different analyses are going to need different resources, that the analysis for different domains will be performed separately, that the analysis can affect one another, and that eventually we have to compose the analysis and the results. So we propose to use the notion of world types as a way to separate the universe of worlds into subsets, and we do that based on resources. So a world type is defined in terms of the resources it includes. And with that, then we can say that a modal operator applies to a world type. So for example, we can say box TA, which means that A is true in all worlds of type T. Let's go back to rate monotonic analysis as an example of how world types are used. And one result of RMA is that given the assumptions that all tasks have rate monotonic priorities and that the total utilization is less than a known bound, then it supports a claim, it proves a claim that all tasks will meet their deadlines. We can express all that formally in predicate logic. So here we can see what are the resources that RMA uses. It uses task periods, task priorities, computation times, response times, and deadlines. So all those elements are the resources that RMA uses. And that allows us to express more specifically, like we see at the bottom of the slide, that the result of RMA, that deadlines are always met, has the strength of box in this case, but applied to the world type RMA. And another implicit aspect of this expression is that this guarantee is true regardless of the state of all the other resources associated with all the other analyses. So let's go back to our example. And now here we have annotated the modal operators with their world types. We have A1, the world type A1 for analysis, for the safety analysis, and the world type A2 for the simulation. Now, if we look at the top, we can compute the strength of that claim in two ways. We can keep the strength level or the mode for each of the claims composed. So in this case, we use a composition of results to preserve that result. So if the claim is if the drone completes the mission safely and on time, we preserve that we have proven that the drone completes the mission safely always, and also we have shown that it's possible to do that on time. If we need to compute a single strength for a claim, we can do that, and we do that with this special conjunction where we combine the two claims, and in this case, the resulting claim will be a diamond G3, meaning that we have shown that it's possible that the drone completes the mission safely and on time. Now let's look at a slightly different example. In this case, we have changed the lower left part of the argument, and instead of having a safety analysis, we have safety testing. So instead of having a result that the system is always safe, we have a result which is diamond, meaning that we have shown that it's possible that the drone completes the mission safely. So if we look at the top now, whether that composition or conjunction of results is possible depends on the world types A1 and A2. An interesting result is that the stronger the claims we are composing, the easier it is to compose them. So if we have the conjunction of two claims that are necessary, that means they are boxed, it's always feasible to combine them and put them together. However, if we have a conjunction of two claims that are possible with diamond, that conjunction is feasible only if the analysis that produce the claims agree on the resources that their world types share, and all the other resources are disjoint. One way to see this in an example is suppose that one of the resources that these two analyses, the testing, safety testing, and simulation use is the velocity of the drone. And let's say that the safety testing was done with the drone flying at low speed, and the simulation to see if the drone completes the mission on time was done with the drone flying at high speed. Then it doesn't make sense to combine these two together because we cannot say that we have shown that it's possible to complete the mission safely and on time. So this is one of the results that came up with the proofs for modal logic rules that within this project. And we have rules for when we can compose claims and assurance results, and how to do that. Let's now go to this second part of the approach, which is about checking the conformance of the runtime behavior of the system to the assurance argument. And we will focus on physical correctness. Many DoD systems are cyber-physical systems, meaning that they interact with the physical world. They have the typical quality attribute concerns like safety, real-time performance, logical correctness, but in addition to that, physical correctness is important. The dynamics of how a system moves through the physical world is obviously important in this setting. And one reason we focus on physical correctness for checking conformance is because if one of the other quality attributes is affected, that will be reflected in the physical correctness. In this project, we have seen that scientific machine learning holds potential for contributing to assurance of physical correctness. So what is scientific machine learning? Scientific ML involves incorporating scientific principles, for example, those codified in differential equations, into deep learning models. There are different parts of scientific machine learning. One of them is what it's called physics-informed neural networks, or PIN for short. A neural network approximates a function, and in this particular case, the neural network is trained so that it approximates the solution to a differential equation. Another area of scientific ML is what it's called the inverse problem or inverse PIN, in which, given that we have a differential equations that have some parameters, and we also have data that we have collected from the system at runtime, for example, we can compute what are the parameters to that differential equation that fit the data. And a third area in scientific machine learning is what it's called operator learning. And in this case, we are solving for families of differential equations by approximating a mapping between two function spaces. And that's called depot nets. That part, operator learning, is where the focus of this project has been in the use of scientific machine learning. So an operator is a mapping between two function spaces. So for example, a mapping from a function on the space on the left to a function on the space on the right in this diagram. A deep operator network is a neural network that approximates this operator. There's this theorem, the universal approximation theorem for operators, that says that with a specially crafted dot product, we can approximate that operator with an error that can be arbitrarily small. But in addition to that, it gives us the structure that the neural network needs to have. So it has a branch part of the neural network and a trunk part. And we have used depot nets in this project to predict the trajectories of the drone in real time, because that's key to runtime conformance checking of physical correctness. So in this case, we want to have an operator G that maps from the space of control functions to the space of trajectories. Control functions are the controls we apply to the drone, physical controls, and then the trajectories are the trajectories that will result from applying those physical controls to the drone. So we use depot nets to approximate that operator G, and that enables fast checking of the system behavior against the nonlinear dynamics of the system. And this is important because flight controllers use a linearized model of the system, but in this case, we can use the nonlinear dynamics of the system to do the conformance checking. Here, there's a chart that shows results of an experiment we did to track a desired trajectory using depot nets. In the chart, there's a blue curve that represents the desired trajectory. That blue curve is mostly covered by the orange curve, which represents the solutions to the differential equations that are used to track that trajectory. But the interesting part is the green curve that represents the result of using depot nets to track the desired trajectory, and we can see that it does that pretty well. A couple of important things to note. One is that the depot net is trained once, but after it is trained, it can solve a family of differential equations. So the way we track a trajectory is by continuously changing the set point and therefore the specific differential equation to track the trajectory. In addition to that, this is very fast and can be done in real time because the neural network has been trained offline, and at runtime, we only need to do inference with the neural network, meaning just a forward pass through the network. So DeepONets allow us to check the physical correctness of cyber-physical systems. To conclude, and as a summary, this work aims to speed up the assurance of evolving large-scale systems through reuse and rapid integration of diverse assurance analysis, and with rapid detection of non-conformance between the system behavior and its assurance argument. We show that modal logic can be used to do sound compositions of results coming from different analysis worlds. We have rules for when they can be composed and how. And we also show that the assurance claims can be checked against runtime behavior. And in particular, we did that and showed that for checking of physical behavior in real time. This is the team that worked in this project. In addition to the SCI staff, we had external collaborators who are experts in logic and control. Thank you so much for your attention.